Hello students. The next topic is gravitational force of a sphere, and we will be also discussing the acceleration due to gravity and weight. So in the Newton's law we describe the interaction between point particles. We have not extended that theorem into large extended bodies like Earth. So in here we will be studying about what is the gravitational force on a on Earth or from a body, an extended body like Earth. Okay, the gravitational force on a particle due to an extended body like Earth can be calculated using superposition principle. So according to superposition principle, forces can be added vectorially to get the total force. So we can assume that a massive body into infinite number of tiny point particles, and we can find out the total, the sum of the forces, individual forces made by individual point particles, and by superposition principle we get the total force of such an extended body towards some another body. So this is our principle, superposition principle, by the help of which we find out the gravitational force due to extended bodies. Okay. So we want to calculate the force between a particle of mass m and a uniform thin spherical shell of mass m and radius r. So this is our mass capital M, which has a uniform, it is a thin spherical shell of mass m and radius r. Right? Now this is the small m mass. So we have to calculate the force, gravitational force between this high mass and this small mass. Okay, so the result is F is equal to minus G, the two masses m into m by r square into r, or r is the distance, the vector radially outward. Okay, and the force has a negative direction and it is an attractive force towards the center of m. This happens, the value of this exists when r is greater than r. Here r is the radius of this spherical shell, and if this r is when greater than r, capital R, this is the value for the force. And when r is less than r, or the radius, the mass is inside this mass, the force will be equal to 0. This is the forces on different positions, where r is the distance from the center of the shell to the particle. If the particle lies outside the shell, that is r greater than r, the force is the same as if all the masses of the shell were concentrated at its center. This is similar to the case when the whole mass is situated at this central point, since m into m by r square is taken. Okay, and if the particle lies inside, the force vanishes. Okay, this is our conclusion. Now, the reason why the gravitational force vanishes inside a spherical shell can be seen by a simple argument due to Newton. Consider the two small mass elements, and it's marked out as a conical surface with an apex at m. The amount of mass in each element is proportional to its surface. Okay, of its surface area. Amount of mass in each element is proportional to its surface area. So the surface area increases as distance square. Okay, however, the strength of the force is inversely proportional to distance square, where the distance is measured from the apex to the shell. So these two effects cancel each other. When area goes on increases, the strength of force goes on decreases. Thus, the forces of the two mass elements are equal and opposite and cancels. We can pair up all the elements of the shell this way so that the total force on M is 0. You can assume that the total force inside the mass is 0. Now we take another example. Although the Earth has a dense core, the mass distribution is nearly spherically symmetric. Okay, we assume this is the Earth with mass me and radius re, which is having a uniform mass distribution, and it is spherically symmetric. To a good approximation, the gravitational force of the Earth on a mass m, this is mass m, at a distance r from the center, is given by F is equal to minus g me which is the mass of earth, into the mass m by r square into unit vector r, where r is always greater than or equal to re. So this mass from the point on the surface of the earth towards the outer space. Okay, m is the mass of earth and r is its radius. So this is the equation for the force, gravitational force of the earth on a mass m at a distance r. Next we find out what is the acceleration due to gravity. We have found that at the surface of the earth, gravitational force on mass m is equal to F is equal to minus g MEm by re square, where re is the radius of earth, re square. We know that the acceleration due to gravity A is equal to F by m. Therefore, when we divide this equation by m, this m get cancelled and get acceleration due to gravity is equal to minus gme by re square into r. Okay, so as we expect, acceleration is independent of mass. There is no value equation, there is no term m here. It is independent of m. The acceleration due to Earth's gravity is gme by re square is universally designated as small g. When g is written as a vector, the vector is directed downwards towards the center. So the vector equation is g is equal to minus gme by re square into r, unit vector r, and this is directed towards the center, hence the negative sign. Now the value of g varies slightly over the surface of earth, but if high accuracy is not required, it can be taken to be the value 9.8 meter per second square or 980 centimeter per second square or 32 feet per second square. Now what is the variation of g with altitude? This effect is easily calculated for values of h that are small compared to Earth's radius. So we can write delta g is equal to g re plus h. So the value of g at a height h above the Earth's surface minus g re. So you get the relation as approximately equal to h dg by dr, the variation of g with respect to r, where we have to evaluate the derivative at re. Okay, so then the result is delta g is approximately equal to minus 2 gme h by re cube. But gme by re square is small g. So when we substitute small g, you get the equation as minus 2g h by re. Or delta g by g, you get the equation as minus 2h by re. So this is the fractional change in g with altitude. Since it is a negative sign, it decreases with h. Okay, when h increases, the change in g has a decrease in the value. Now the earth radius is approximately 6 into 10 raised to 6 meter, and so g decreases by roughly 1 parts per million for each increase in altitude of 3 meter. This is the rate at which it is decreasing. Next is the weight of the body. So actually the weight of a body is the gravitational force. It is the gravitational force exerted on it by the earth. Okay, at the surface of the earth, the weight of the mass m, or the weight which is the gravitational force exerted on the surface of earth, is equal to minus g m by re square into r. So this value gme by re square is g. So weight is equal to mg. So actually weight of a body is equal to the gravitational force exerted on it by earth. So W, the equation of weight, is equal to mg. The unit of weight is Newton. In SI unit, CGS unit it is dyne, and in some other countries it is pound. Okay, so this is the definition of weight.